Hello, and welcome to the FlowCAD webinar, Detect and Eliminate Design Errors at an Early Stage. My name is Petra. Today I'm supporting my colleague Dirk Lindenbrugger. By using practical examples and typical PCB designs, he will demonstrate the targeted use of the SI and PI workflows included in Sigrity X Aurora. If you have ever had contact with our support or attended a training, you probably already know our expert. A few words about him. Dirk studied electrical engineering with a focus on communications engineering and has in-depth knowledge of various software products from the EDA environment that cover signal and power integrity, as well as thermal-aware electronics applications. Our cameras will remain off to avoid technical problems as far as possible. That's all for the moment. Dirk, let's get started.
Okay, thank you, Petra, for the nice introduction. Welcome to our webinar. Today, I'll share some methods to you that can be used to detect and correct avoidable layout errors early in the design process. The idea behind this so-called shift-left approach is new, but in our opinion, it's used far too little. It's relatively easy to perform various SI and PI analysis, also signal integrity and power integrity analysis, during the design phase without leaving the PCB editor. I'll introduce the various workflows to you in this webinar. So the advantage of these easy-to-use checks is that you can review previously routed areas during the design process without having to leave the PCB editor. The checks can be performed by PCB designers without any assistance or without less assistance of SR or PI experts. In my opinion, this is a very important point as it reduces potential stress between the various team members. It also means that subsequent layout reviews can be reduced significantly. And because the design cycle can be shortened, you can achieve your time to market goals more easily. So first, I'll start with the workflows that have been available for some time and that you may already be familiar with. Please note that the impedance and coupling workflow is also available in ORCAD Professional without additional licenses. I'll then give a brief introduction to the other signal integrity and power integrity workflows. Due to time constraints, I can't give you an insight into the powerful extraction workflows today. We are planning a separate webinar for this in the near future. So to successfully use the Sigrity Aurora design workflow, you first need to make a few entries in the PCB database. First here, the layer stack-up must be correctly defined for signal integrity analysis. Then for power integrity analysis, the DC nets must be assigned. Finally, you need the appropriate data for thermal analysis. In the hands-on workshops mentioned here, I'll show you the necessary steps in detail and provide additional background information. Just take a look at our website, flowcad.com, under events and then hands-on workshop. The next, I want to show you a combination of some slides and also a live demo. I hope that works and that doesn't crash it anymore. So because we start at the first with signal integrity issues or tasks, what is the main purpose on this? Yeah, we have impedance discontinuities that can create reflections, and on your signals, that means we have reflections, ringing, and so on. And maybe this can also disturb your signal quality. Finally, in addition, we have to check the coupling with responsibility crosstalk issues or effects on your PCB. That means that no signals are coupled into victim lines. How can we do this? Now I want to show you how to set up at first the impedance scan. So it's quite simple. So as I already mentioned, you have to set up the cross-section before starting the simulation, signal integrity simulation. Then you select some nets. Maybe it's an option to modify some simulation options, run the simulation, and as finally you get some tables and the so-called overlay visions that gives you a very fast overview of where some problems can occur. So in principle, that is what the tool can do, and now I want to try to show this in the first design here. Okay, let's get started here. I open the file. This is let's start here with the impedance workflow. Oh, I don't want to save any files. Oh, what's that? Sorry. Yes, please go on. Okay, start again. At first, now you can select some nets. You can either select all from this list, or even some selected nets. I've done this in pre-OR, and because the simulation of a complete net list, what it includes about more than 500 nets, will take about several minutes. I think about 4 or 5 minutes, and therefore I prepared already the simulation results. As you can see here now, we have an impedance range from, let's say, about 10 ohms to 145 ohms. What does that mean? Okay, we can see here in the top, there are some traces that have about 10 or 28 ohms, and we can see, okay, that is something ground that was also selected here, which is not a signal net, but more or less a power net, and therefore we can ignore that. We can use this slider to more or less fast identify so-called hotspots on our impedance. That means our nominal impedance is about 50 to 60 ohms, and when we use this slider, we can hover here and see where potential hotspots are. And in this case, here we can identify them very fast. We can also switch from single-ended to differential pair, for example, and then we can see here that we have some diff pairs here in the memory interface and some USB traces over the board. Okay, but now I want to go back to the single-ended nets and have a closer look to those candidates that have here a very high impedance of about 180 ohms. And let's see why this could happen. Therefore, I select these 3 nets that are highlighted here at the moment, say, okay, apply, and already run the simulation for only these 3 nets. You can see it's quite fast, and in the behind, the tool checks out the solver, the hybrid solver from Sigrity Power SI. I come back to those point tools a little bit later on. So now we have the result already here in hand, and we can see that we have a very high impedance range here over this area. We can also use the tables, and we can select, okay, this is the net we are interested in, and we can change the impedances so that we can see how long are these C-line segments, and when we double click onto one of these segments, the cursor automatically jumps into the design, and that makes it very easy to identify or to find where these discontinuities come from or arise. So when we also switch on the reference layer below, we can see, this candidate has been routed a very long way over a split in planes. And therefore, of course, we do not have a reference, the direct reference plane below this signal trace, and that makes it that the impedance grows up such significantly. Now, it's your task from the PCB designer to now you find these signals, and now you can just easily move the traces away from over, let's say, to a solid ground plane or to a solid reference plane, and then you can directly rerun your simulation and to see how that would behave. So done, okay. Rerun the simulation. Now I don't want to save the result at this moment here. Just see what happened here. Please remember that we had an impedance of 180 ohms before this modification, and now we can see, okay, here we are in the nominal impedance range. I think that is very, very fast and quick check to identify potential discontinuities and how to correct them. However, we also see that we all still have here some very short gap where we have routed over this gap. And I want to come back to this issue a little bit later. But at this moment, we cannot change it in a better way as it is in this moment. So what we can do now is, give me a second, I want to switch back to the slides. We have now seen that we can directly optimize here our design, remove shift away the signals to a solid ground plane. And if you want to see what happens with the signal or waveform itself, you can use the so-called reflection waveform, reflection workflow. In this case, we have to attach IBIS transceivers that enables us to do real transient analysis. These IBIS, we have a couple of IBIS transmitters are coming with the installation so that you can choose between, I think, 3 different types that cover the 3.3, 2.5, and 1.2 volt technologies, and different rise and fall times, of course, can be assigned, and of course different data pattern. And as a result, now you can see the waveform that is created from the driver to the receiver side. And in this case, we also can see once we move away the trace from this gap over a solid ground plane, we can see that the ringing has been reduced, yes, more or less significantly. I think that is a very good way to do this. However, if you have vendor models, you also can attach them instead of using these default models. And then, of course, you have a better waveform quality because it's more or less related to your vendor models. Okay, as next, I want to follow up here with a coupling workflow that is also available from the ORCAD professional license, if you have this. And the beauty of this coupling workflow is that it does not only detect issues in the horizontal plane, but also in the vertical plane. That means, of course, for example, here in this case, once we have a so-called dual sandwich layer stack-up, it also detects areas where signals have been routed in parallel over each other. And that is something that is very, very difficult to identify if you have if you do let's say a layout review afterwards. I want to show you how this could work right now. Now I switch over to or I load the corresponding file. It's always the same, but I want to show it to you here in this case. No, I don't want to save. And in this case, I want to create a different way of creating the nets. Previously, we had used here selecting nets, but we also have the option here to select here so-called directed group. And in this case, this is already done here. I want to delete it. And then say apply, okay. In this case, it is quite easy to select only, it's still there, the driver. For example, here we have this U6, that is the controller, the memory controller. And in addition, we also select the U4 and U8. These are these memory devices. And with 3 clicks, you have selected the whole simulation signals. And then you can already start the simulation again. I've already did this before because this simulation of, let's say, about 60 to 70 nets also takes a while. And here now we can see, not on top side, but here in the inner layers, inner 3 and 4, we can see that we have a lot of traces that are routed directly in parallel over each other. And now you also have this chance here just to make it easy to remove such signals here to avoid crosstalk issues. Yeah, you can just move them away here slightly, and as a next step, you can see, well, this reduces the effect of coupling in this area, and then you are very fine, and you do not have to let's say, to discuss with some colleagues about crosstalk issues. And if you now rerun your simulation, you will see I've do this in this case, and I use the modified design, that the coupling here in this area has been also reduced significantly, and that gives you the opportunity from the PCB designer perspective. Yeah, once you have done a certain part of your design, run this check and modify or correct some issues as good as possible. And then you do not have to care about that. It's more or less at the end of your PCB design, once more or less everything is finished. I know that's a very good way to achieve a very good robustness in your design without a lot of effort. And here we can see in this design how this can be done. And once you, of course, I know that it's not always possible to move away all signal traces from each other. Then we have the chance, the option here to use the so-called crosstalk workflow. This crosstalk workflow works similar to the reflection workflows by attaching IBIS transceivers, so that you have here a real waveforms that can be analyzed by selecting only a few nets, not a complete bus in this case. You only select a few nets, and then you can see how the crosstalk effect can be optimized. In this case, we were able to reduce the amplitude of the injected voltage of more than 90% just by moving some slides away. And I think that is also a very, very good and easy way to achieve a very robust design in this case. Okay, once this is done, I want to follow up, with some more workflows that are related to power integrity. What are the main topics we have to take into account when we talk about power integrity issues? Here with related to our Aurora analysis workflows, we have some workflows available that can help us to identify at first the so-called AC or the resistance of your board. That means we can do a so-called DCIR drop analysis that calculates the voltage drop from the voltage source, the voltage regulator module, VRM, down to your sinks. That means to the loads. And because of these resistive effects, we got a voltage drop, and that maybe also can have the effect that shifts down your voltage level lower to an allowed level for your devices. And in addition, we also have to cover so-called AC effects. That means we also have to cover here some parasitics in your design, creating some noise on your power delivery systems. That can be the root cause can be different ways, but we have in this case the possibility to analyze the distance from your decoupling capacitors to your supply pins of your voltage. And we need these decoupling capacitors to reduce this noise. And this is a very, very easy way to find how we can do that. And finally, we also have a new workflow that covers thermal, but we will see that a little bit later on. So in principle, the workflow itself, the step setup is similar to the signal integrity workflows. But here, as mentioned in the introduction, we have to identify the DC nets because we want to see now, we want to analyze these voltage rails. And then, of course, select the nets, set out the voltage regulator, run the simulation, voltage regulator and things, with respectively the loads. And then we can see what happened on our design. At first, I want to start here with this IR drop analysis. Yeah, then I will show you how we can do that. In principle, once we use, or if I come back here, set up the voltage regulator for a power rail that has the same name over the complete net coming directly out of your voltage regulator net, then we can use a wizard. So we only have to select the voltage regulator and select the power rail, and then we already can start the simulation. But once we have more complex designs, that means you have some filters, design filter schematics out directly after your voltage regulator, like inductor, capacitor, or whatever else, and a lot of unnamed nets. Then you need. Then I would suggest to use the so-called power tree. I will show you how that works, and this is a very powerful tool to set up complete voltage rails. And as a result, we can see here that we get this colored overlay, but also we can use the current density on your design. And with current density, you will find a lot of issues that it's very easy to solve afterwards. So, okay, what is the power tree? In the power tree, you load the complete design, and then you can create define so-called through components. For example, here we have this U2, which is our voltage regulator, and then here we have an inductor as a so-called through component, and then this expands the complete power tree. And now you have the chance, the possibility to optimize or to define all of these things and loads, but you also have can simplify if you want to do this. Furthermore, you have this. This power tree also supports DC-DC and LDO drivers configurations. I want to show you how that works now a little bit in practice. I'll start here with a new file. Let's create a new file, and here you can see that you can also do this. Use this power tree from system capture, for example, directly in the schematics development or schematics design. So in this case, I would also say, okay, the designer can create already this power tree for the PCB designer, and that makes it easy afterwards for the PCB designer just to load this power tree file and run the simulation directly without any more effort. Now I want to open here this BRG file, the Cadence board file. And use the same board as we have used just previously. Now it's loaded into our power tree, and at first here we can select some nets that goes from the voltage regulator. But I want to use, I want to continue. No, and I want to open this field. The positive pin in this case, I want to assign our voltage regulator output pin. You can see the complete design list, and here I want to select U2, as you mentioned, that is our voltage regulator, and pin number 15, that is the voltage of the net 3.3, which I've just add here in this case, and then it is done. As next, we have some options here to create or to identify some things with the different reference designators, and also we can define so-called through components. I leave that at this moment as it is, and just click the build tree button here. Now it opens a through component which is representing a transistor. That can also be defined here, input and output pin, but I say, okay, I don't want to use this in this case, and the next transistor, I also do not want to use it. And this expands the complete power tree. And I think this is a very, very easy way to select all these ways. Now we can say, okay, this inductor has an internal resistance of, say, okay, 10 millivolts, for example, and then it is included into our complete current net here in voltage rate. And if you say, okay, I don't want all of these branches that are really not useful at this moment, you can say, okay, I want to cut off branches, and you can delete them. And therefore, it's easy to optimize or to identify or to simplify all this design. Here we have this connector U2 pin number 17, that is the input feedback line, and then we say, okay, we want this as a sink, we disable it. It's also a way how we can define such properties. And finally, we can double click here on the things, and then we can say, okay, this candidate has a current here, let's say, okay, so for 1 ampere for all 5 pins, that is distributed in an equal way. If you have, for example, big processors that have many 10 pins and that needs unequal current, you can also use, okay, 5 pins have 1 ampere, and another 5 pins have 5 ampere or whatever else, so you can even assign them as an unequal way. And that's all that you have to do by creating this power tree. I want to open this now, and I want to save it. As we use it, that is now the final tree that we want to use for the next simulations. Here we also have the connectors, for example, that can also be used as voltage sinks. Now I want to go back into our design itself. So give me a second. I use this one. Here we have an impedance worker. Okay, now I want to open. No, sorry. I open the IR drop design. It's always the same, but I want to have here a fresh design, and then we change here to IR drop workflow. At first, I want to show you once we have a simple wave where we only have the voltage regulator. For example, in this case, I can sort the voltages here, and this one I want to use the VSys 5 volt, and that directly shows me all available components that are attached to this power rail. And here we have our U2 as our voltage regulator, and say okay. And the things is quite simple. You can also select all that are available here. So, but we also want to select only these 5 voltages, 5 volt here, and the current that is already attached in this case can be defined as a default value. I made it simple here. I've left here this 1 ampere, but you can do even what you want, and you also can edit them here if this is necessary. And then you can directly start the analysis. That's all that you need. And you can see that the simulation also runs very fast. In the background now, the so-called power DC tool is Sigrity Power DC is running, and we are already done. So now we can choose here the voltage visions, and here on layer 5 we have the main region where this power is delivered. Okay, that is a simple way, but now we want to change here to use the power tree. As we've already learned here, we have this created this power tree already. We use the 3.3, and we can also run this simulation directly once we have loaded the power tree. I think this is a very, very fast way to achieve to get the results, and you see how this can be done. Here we can see now the IR drop, or even the voltage or current density. I come back to the current, or let's leave it here to the current density. Go back here. Let's say, okay, IR drop. We can see here in this region we have our voltage regulator. The voltage is distributed over the complete board, and we have a voltage drop about 65 milliwatts, which is quite a lot, I think. And here we can see, okay, here we have a very small path where probably the high voltage drop will be created. Once you do not have this, and we only have to do such analysis in a layout review, you may see, okay, here, this is our 3.3 power rail, but it might be very difficult to identify that this region is very, very creates such a big voltage drop. I switch it on again, and now I want to switch on the current density, and then we can see, oh, here is something where we have a lot of current, and here also in this region. And now we can also identify that this additional vias makes the path even smaller than expected. And this, when we switch on the vectors as well, you can see how much energy will be created in this region. And this may also not only create a voltage drop, but also can create a heat. That means, that in this region, the copper will be affected by additional higher temperature that can cause on a long term that the reliability of your PCB will be damaged. Now I switch off the visions again, and now you have the chance directly to change the shapes here, for example. Switch on to shapes. For you as a PCB designer, it's quite easy, of course, to modify these shapes. I have prepared it so that we have now a wider range here, and we can directly rerun our analysis. No, I don't want to save the results in this case. We remember we had about 65 millivolts of IR drop, and now we can see that we have a maximum of 55. That means we have relaxed this region significantly. When we enable the vertical range here again to 65 millivolts, we can see that we have completely relaxed our design. As we have seen just a few seconds before, there was a region where we also had a lot of current here in this region. So let's have a look what happened here. Maybe we go to the top side, and we can now switch over again to the current density, and we can see, oh, what happened here. This is our voltage regulator, and we can see, oh, in this case, we have maybe a very small path for the connection from our output pin over to this inductor. This can be optimized, I think, also a little bit by wider traces here in this range. What we also can see is that we only have one via that has to bring the complete current from the top layer into the inner layers. And that can be overstressed over the time, maybe. And that helps us now to also to modify this. Switch on the design again. So what we can do now is, now switch off, that we maybe also can, where we are here. Sorry, oh, I am on the wrong layer. So let's switch over here to the top layer also here, from loud writing layer. Now, what we can do now here is that we maybe also add additional vias here. So, oops. And so I don't want to do this. I want to copy only this via and say, okay, let's do it, and place it over here maybe, and also place it here. Now we have added 2 additional vias, and we can see how this would behave now to the current distribution. You see, it's a quite fast way to do this kind of what-if analysis, and we can see, okay, this via helped, and this via here below has more or less no impact to our current distribution. And when it has no impact, then we can delete it again. We can move it to another place so that we have a smoother current distribution at this region where the current has to be transferred from topper to lower layer to the inner layers. And I think that is a very, very nice feature that helps to bring up your design and make it more robust overall. Here again, we can see here's a summary of those steps I did so far. Now we come to the power inductance workflow. As mentioned before, this calculates the distance from your decoupling capacitor pins to your pins here from your devices. I know it also from my past that this is a very difficult job if you do that only with the 4 eyes principle. You see how there are many decoupling capacitors located around your devices, but it's hardly to identify how far they are and if they're really working. As you know, once the decoupling capacitors are too far away from your devices, they do not really work. So that you can either delete them because they have do not have any impact to your design, or you can optimize your design by moving those capacitors closer to your IC pins. So the design server itself, how the setup works, I want to show you here right now again. Let's open this design. Now let's leave the IR drop and open the inductor workflow. No, I won't want to leave it here. And here the setup is almost the same for inductance. We select the power rails that we want to analyze. For example, here we have the 3D walls again, and only have to select the ground net, the corresponding ground net, and the tool itself directly searches all those capacitors that are belonging to your design. Here in this case, I did not select all devices that are assigned to this power rail, because then you have sometimes several hundred capacitors. But now I just want to have a look to this device here on the top left side. Therefore, I've selected U1. And this selects the corresponding capacitors that are located here around this device. And the simulation also takes a few minutes, and therefore I've prepared that already. And once we switch on the visions, we can see here, okay, we have one of those candidates here that is marked in red. That means 3 nanohenry, and we can also, I see that is quite far away. Typically, once we have an inductance of less than 1 nanohenry, that is quite good, because 1 millimeter, you can say 1 millimeter of traces is responding to 1 nanohenry of inductance. Here we have some values that are below. That means in this case we have, for example, capacitors that are located under the device, so that is has a very short inductance. But in this case, we see, okay, we have these two candidates, and that might be optimized. And once we say, okay, let's move them a little bit around here, symbols, okay, we can move these devices to over here, and the next more or less very closely, so that we do not get any DRC errors. And then we can rerun the simulation, the analysis. I do this, and we can see that this helped significantly. And once we open the tables again, that we have reduced for this capacitor 206 from more than 3 nanohenry less to 1 point, or in the range of 1.6. And we can also do this in another loop to optimize the distance, maybe also a little bit more. So that is a very easy way and quick and fast way to optimize your the placing of your decoupling capacitors. I hope that is clear so far. So I really like this tool, and this opens the power optimized PI tool from Sigrity that is more or less specialized for doing such kind of analysis in the terms of power integrity analysis. And finally, we have the thermal workflow. It is quite a new one, and that helps for example here in during the layout phase. The beauty of this tool is now, this workflow is that you do not need completely routed nets. You do not need a complete that the board is completely electrically routed. So you only need some copper planes that can distribute the heat from the top layer down to the bottom layer. And here in such placing studies, we can say, okay, we have these 3-4 devices, assign them power dissipation value, and then we can directly start the analysis. And we can see, of course, here in this case here, that is the pre-layout status. Let's say, okay, here the devices are very connected very, very closely to each other. Then we move them slightly away because we also have to do some routing between these memory devices. And here we can directly see, okay, we have the temperature relaxed slightly. And finally, you can do more or less, depending on your layout status, once there are more and more layers routed, that of course increases your accuracy of the temperature distribution in the complete design, and you can also do some what-if analysis. What we did here from step 2 to the final step, we also modified the kappa thickness, especially on these power planes. We started here from half an odds kappa thickness, it means 70 micrometers to 1 odds, that means 35 micrometers. And we can see how that has an impact to the power temperature distribution of your components and also of the kappa. And that is something that may really help you to do such what-if analysis very early in the design to get a feeling about your components if they get overheated, or you can say, okay, maybe it's even better to spend a little bit more money for our PCBs by spending thicker kappa layers. But in this case, we can leave out the necessity of additional heatsinks for our devices. And that is something that I think is very, very helpful here, especially in the pre-design phase, to identify, to define the final layer stack-up and also to see how that works in the complete design environment. And last but not least, we also talked about the return path. Once you remember to the beginning, when I showed to you the impedance matching or impedance analysis. Here, for example, we can see how this return path can be visualized with this workflow. The background of this return path analysis is, in principle, once we have high-speed signals, what is high speed? Let's say signals starting at 50 megahertz or even maybe a little bit lower, and of course, that never stops in the frequency range. The return path directly is located underneath your signal trace. But once the signal trace is interrupted, or the return path, the return path, so it means the reference plane is interrupted. So the return path has to search a way through your complete design, and this is more or less unpredictable. And with this return path workflow, it is possible to visualize the return path. Here, these images you can see, okay, we have a nice return path directly below our signal traces because we have a complete reference plane. But once we have here such holes in what happens here with our return path, so it searches some vias and to create a closed loop, a current loop, and you never know where this return path now goes, where the current goes through your design. So in principle, it can go through the complete design just to close the loop, the current loop. And in this case, it can select a lot of noise from all other planes. But it also cannot collect noise. It also can create noise to outside. And that is essentially the point where it makes sense to talk about that you should not route signals over such split planes. We can see this, I think I opened this in this design. Okay, here we can see we have a nice way that the current directly is routed over here this signal. But now it stops because we have these signals that are coming that have no reference layer below. And now we have to see, well, where is my reference? Where is my current? My current? So we can go through the different layers. If there's nothing. In R3, okay, here we have something that means we go from layer 5 to inner 3, and we can see here ground on layer 2. There's a big way where the current goes. So you see, in some cases, the current goes through your complete design, and you never know exactly to which vias can be used or will be used, and that makes it even so difficult to say before where you should go. And what happens here in this case is I extracted this net with Clarity 3D solver to see what happened. I used this way. This is not included into the Aurora simulation environment, but I wanted to show you the effects. And here you can see the far field effects. On the left side, that was the initial design where we have our signal routed over this long way about the split in the planes. And on the right side, you can see a significant reduction of the level, but not only on the higher frequency range, but also here on the lower frequency range. And if you think, or if you go into your EMC tests, and then you get some stress because you fail your EMC test because some of your devices create too much noise. It is very, very difficult to identify such issues where it comes from. And if finally you have to have identified such cases, this directly leads you to a complete redesign that costs a lot of money for time, the redesign itself, and of course for an additional prototypes. And therefore, it's not only a myth that that you should not route over the splitted planes, but here we have a proven way. And if you really can avoid such things by checking, for example, the impedance, move them around, move them away from these split in planes, maybe attaching some additional stitching via, ground stitching via, so that the return path has a better way to directly follow your signal current, then you are fine. And I think that will significantly increase the robustness of your complete design. So now we come more or less, that's done now with my the live demo. And now I want to summarize here what we have seen today. And in principle, the Sigrity Aurora is it bridges the gap between your design and the analysis. That means the design, PCB design, and analysis. And by directly using some signal integrity, power integrity analysis. And again, it's quite easy to use them. You do not have to leave your PCB PCB editors, and that's something that you should take into account in this case. And I'm pretty sure once you follow some of these workflows, that will improve your performance of the design and also will reduce your design cycles. So in principle, in summary, today I've introduced you the various methods that can be used to analyze, to optimize during the different design stages. So during the layout design process, you can perform the comparing signal integrity, power integrity analysis so that you can optimize your design. So after all, that is something that you should take into account. You cannot damage anything with simulation, so you can also develop new innovative solutions in this space. So in this way, you can increase your product robustness and accelerate your time to market. But now, before I finish this webinar, I would like to give you a short overview to the Sigrity X token license model. So what is this? So Cadence has a new license model. That means that you can change between the different Sigrity license and you have access to all of them if you want. As you remember, I've mentioned different point tools like Sigrity Power SI for signal integrity analysis, Sigrity Power DC for this IR drop analysis, and for example, Optimize PI for power integrity optimizations related to the decoupling schemes. So that is something that you can do now. So instead of buying or TBL licenses. You can say, okay, I take about 4 licenses. We can see how that is. Sigrity X Aurora, for example, uses 2 tokens. Power DC, Optimize, BI, and so on use 4. And then we have some more advanced solvers that can be used here with some more tokens. But once you say, okay, we have 4 tokens here in this case, you can choose every tool that can be checked out with 4 tokens. In this case, for example, 2 times the Aurora, or even Power DC and Optimize BI, Power SI, and so on. I think that is a very, very easy and powerful way to use the complete available products at different time stages. And that hopefully helps you also to bring up your designs in more reliable way. Once you say, okay, Aurora is not the tool that we need for the starting point, it's very, very useful, but we want to dive into more details, then you can use this token model, for example, here to either dive into more power integrity analysis or thermal analysis, or for diving into more signal integrity analysis, also including some more interconnect extractions, depending on your frequency range. If you have working with power answer PCI Express Gen 3, then it's maybe okay if you use the Power SI with 4 tokens. So the instruction goes up to several gigahertz, let's say 5, 4, 6, 7, 8 gigahertz, then it's very accurate. But beyond this, that means if you go into the right direction, for example, into PCI Express generate 4 and 5 and so, which goes up to 40 gigahertz and beyond bandwidth, then you need the 3D solver. It's the same also here with the serial link analysis. Depending on which data rate you are working, you even can use them in related with the extraction tools, and this parallel bus serial link analysis helps you to identify, to analyze all of these stuff. If you want more information, we are happy to share this information to you personally or individually, let's say in this case, because it's just an overview to give you an impression. So to say, okay, hey, there's something that might be interesting for us also for next time, where we can use, where we want to change, for example, some products, or we want to add some products, and then we will be happy to talk to you individually about all this stuff. As already mentioned, we have some application notes on hand. Just have a look. You get, I think, the slides as well. But if you go to our website, flowcad.com, and then download and the application notes, you can find the setups for the impedance and coupling workflow, and also how to define the cross-section editor. And in addition, as I've also mentioned, we have some online hands-on workshops on hand, defining, or where I go into more details about the setups with the coupling, impedance flow, coupling and impedance workflow, as well as the IR drop and power integrity tools. So now I want to finish my presentation, and I thank you for your attention. And I am now open for some questions once they should raised up.
Thank you very much, Dirk. Great presentation. We have some topics we can discuss further on. So you have mentioned that the InDesign analysis use Sigrity tools or solvers. Maybe you can describe more, what does that mean, and how can we understand this?
As you know, we have the 2 parts. We have the PCB designer tools, Allegro and OrCAD installation, the so-called SPV tools. And on the other hand, we have the Sigrity tools. And both tools work in this case together. So the Sigrity tools are not only simple mathematical assumptions that use here real 2.5D hybrid and field solvers. So the results that come out are really reliable and very accurate, as you have already seen. And that's why we have both tools here on hand. And once we run one analysis, the Sigrity tools are running in parallel in the background.
All right. Thank you. If I understand correctly, Aurora perform IR drop analysis and also consider thermal analysis of components on the PCB. Can heating of a circuit board caused by high current densities also be taken into account?
Yeah, that is something that I've mentioned when we remember. I've shown you this power rail where we have also these vias included, and when I mentioned, oh, this can also create some heat. Yes, it is something that can be taken into account, but not with Aurora. To do this, to take into account this, I think it's called joule heating. Yes, joule heating. We need a so-called electrical thermal co-simulation. And this can be done with a point tool, Power DC, or nowadays it's called Celsius Power DC. And with this tool, now you can also include thermal aspects that rise up during also in your PCB. Yes, and so not with Aurora, but with these additional tools that can be done.
Wonderful. What copper thickness can be simulated with Sigrity Aurora? Is there any information? Sorry.
Oh,
something very special.
Yeah, exactly. I think I had similar questions a couple of months ago when we talked about also with the Sigrity, the thermal solver. In this case, I was in discussion with Cadence about such things, and I know that about 4 odds copper thickness, that means 140 micrometers, can be solved without any limitations. And therefore, I think since we use this solver, that will also give us here the same results as once we use only this point tool with the Power DC. Once we need some more information, I have to go back to the R&D department to check out if there's some limitations.
Okay, thank you. And maybe a last question, can meshing be visualized?
Oh, that is a nice and funny question. No, not funny question, but of course, yeah, I know many people want to see the accuracy of the design. That means the meshing, but this is also not possible with Aurora. So therefore, we can use this also the point tools like Power SI or Power DC, where we can enable the meshing, but not here in Aurora. As you remember, Aurora is something to be used during the design process without the need of special signal integrity, power integrity knowledge. It's used really as a practical working tool during your design, and use it and don't think about all this theoretical background. If you want to talk about this with some of your specialists, you can do that, but it is not the main intent of Aurora. I hope this makes it a little bit clearer and gives you an impression how the philosophy about Aurora is.
Thank you, Dirk. If someone has more questions about some of the shown topics, or if you are interested in a demo, or as Dirk mentioned, our hands-on workshops, it's very easy to participate. Please just give us a call, send us a message, and we are happy to share all information you might need. Have a great day.